Comes on everyone. So last class we have done with the rigid body constraints. Great. Others comes on. Let's start off. Like I said, the second part is the Newton laws of motion and the free body diagrams. So a bit of a theory. Newton's first law. Now what Newton's first law says is a body continues to be in a state of rest or uniform motion until and unless it is acted upon by a force. So if you see in these words, right, the main thing is rest or uniform motion. So that means, in day-to-day life, right, when you throw something, it actually stops. That is because there is a friction on the ground and air resistance. But if you try to do the same thing in case of a vacuum, when there's no air resistance and there's no gravity, you'll observe the particle never stops. It will just keep going forever. So if you want to start to move something, you need to apply force. If you want to stop something, you need to apply force. So the important thing here is just to move an object, if something is going with constant velocity, you don't need to apply any force. So the first law gives us the concept of force and inertial frame. And what's an inertial frame? It's a frame about which observations are done. We have written that, in kinematics. Now, all forces, right, can be classified into four types. That's it. First law is just a statement there. If you see a practical application of this, look at this. So that's a tennis racket with a lot of dust. Did you see how it got separated? So the thing is, when that ball is hitting the tennis racket, you're applying force on the racket, but not on that sand which is on the thing. So when this hits, the sand still stays there. Then because of gravity, it falls. But if you see at that instant, they both behave like two independent systems. You must have seen, these kind of videos also. People put a lot of glasses on a tablecloth and they suddenly pull the cloth. And nothing happens. The cloth comes out and the glasses are just at the same place. I hope you have seen something like that. Same idea there. It is also based on the first law only. Now, all forces in the universe, right? You can classify them into four categories. There are four types of forces. The first one, gravitational force. Now, these forces are due to interaction between masses. And if you look at the range of these forces, range meaning up to what distance can you interact? They can interact up to infinite distance. For example, if you look at Sun and Earth, the distance is almost 15 crore kilometers, but still Sun attracts the Earth. And if you look at the strength of the gravitational force, it is weak. What do you mean by weak? For example, see the pen you're lifting, right? If you leave the pen, what happens to the pen? It falls down. Who is making it fall? The Earth. That means the entire Earth is attracting your pen, isn't it? And you're simply lifting it with your single hand and opposing the entire Earth, isn't it? When you keep a pen on the table and you're lifting it, you are opposing the entire Earth attraction on the pen with your one single hand, isn't it? So that is what I mean by weak. Even though the gravitational force, right, as an infinite range, the strength is very weak. The second type of forces are electromagnetic forces. So these are the forces due to interaction between charges. Right, and this range is in meters. These are strong forces. The third one is nuclear forces. This is interaction between nucleons. So this is a force between the neutrons and protons inside the nucleus. This is a very small range. The reason why we don't notice this is because these things act at a distance of 10 power minus 15 meters. It's called 1 Fermi. And these are very strong. The fourth type are called weak forces. So these are the forces actually inside the protons and neutrons. These things are still, most of the things we still don't have an idea how these things work. So this is still under study. So you can classify all the forces in the universe into these four categories. What we are mostly interested is gravitation and electromagnetic. We'll not even study nuclear forces. Nuclear force is just a small statement we write in modern physics, but gravitation and electromagnetic is what you're more interested in. There, have a look at this. So that is a little classification of forces. All clear with this? Then, turning the page, like I said, just a bit of theory. Now, in mechanics, we deal with normal reaction, tension, spring forces, and friction. Now, initially, we will study normal reaction and tension. Spring, we will study at the end of the chapter. And friction, we have a separate chapter for it. Out of these four, friction is the most notorious one. It's like a rogue. So it does all weird things. So you need a separate chapter for it. So the first force we will deal is normal reaction. The symbol is N. So how do you get normal reaction? So when two surfaces are in contact, the nucleus of the molecules repel each other, generating a force along the common normal. Now, so when you take two surfaces like this, so this is what is actually happening. Now you need to understand, even though the molecule is, so what you call neutral, but if you look at the nucleus is nothing but a positive charge. So they repel each other. So one more nucleus will repel each other. This molecule repels this one. So if you see, because of this repulsion, you get a force along the common normal. So this repels here, this repels here, this repels here. So when you're actually touching the pen, for example, now you're sitting on a chair, what is actually happening is the molecules on the chair are repelling your molecules. And because of that repulsion, right, you are actually, so the feeling that you're touching something is nothing but an electromagnetic repulsion. You're not actually touching the bench. Think about it. If you actually touch something, the molecules will go so close, the nuclear force will come and they will fuse. You'll get a nuclear fusion and there'll be an explosion. So if you can actually touch something, there'll be a nuclear bomb. So right now, what you're experiencing when you touch something is nothing but a kind of a repulsion between the surfaces. Right? What you're experiencing is that. So a normal reaction is nothing but an electromagnetic force. Like I said, all forces fundamentally belong to the four categories. So we call it normal, but at a fundamental level, it's an electromagnetic force. So the reason why you get normal reaction is because when you put your hand on the table, what you're experiencing is a repulsion between the molecules on your hand and the table. That is what you're experiencing. So what is a common normal? We have written this last time in rigid body constraint. So if you have a wedge end like this, or if you have a wedge and a sphere, or if you have a sphere and a sphere. So whenever two surfaces touch, the force will be along the common normal. So this is the reason why you get normal reaction. So you always need to see fundamentally what is happening, why you get a force. If you touch, why should you get a force? So this is the reason. This is the first type of force, normal reaction. Any doubts on this page? Okay, going ahead. Next thing, tension forces. Now, first thing, when you say tension, you need to understand tension is the state of the material. Tension is not a force. So what is this tension? Why do you get this? So basically what happens when a body is deformed, that means if you take a rod or something and if you try to push it or pull it, when a body is deformed, that is elongation or compression, we say the body is under tension. Mm, deformed, we'll go back to there. The internal restoring forces are generated. Look at the word. internal restoring forces. So these forces are inside restoring. They will try to bring you back to the natural state. Think about it. Let's say in your classes, right? On a bench, three people can sit. If a fourth person comes and tries to push you, what will happen? You'll try to resist, right? Because you're not in a comfortable position. You're getting compressed. You don't like that. You try to resist it. But the moment he leaves, you're okay with it. So you will try to keep pushing as long as he doesn't leave. So that is like an internal restoring forces. These are the forces which want the body to come back to the natural state. So these bodies generate, internal restoring forces which try to restore the body to its natural state. So we can say the body is under tension and the forces are called tension forces. But in all books and everywhere, right, we keep using the word tension, tension for force also. It's like this, when you're angry, you start shouting. Anger is your state, isn't it? Anger, you're being angry is your state of mind. In order to relieve that frustration and anger, you start shouting or you do anything. So both are not same. So tension and tension force are not same technically. So tension force is like a way of relieving that stress. Tension is like the state of the material. So when you say you're under tension or when you say material is under tension, meaning it got deformed. That's what it simply means. We say the body is under tension, but in all books everywhere we will be keep using the word tension. So tension matlab somewhere down the line became a word force. So we'll use that. We say the body is under tension, but theoretically that's what it means. And these forces are called tension forces. So basically, the internal restoring forces is the tension force. So the symbol for tension is capital T. Again, why do you get tension? Again, same reason. When you're pulling, right, the molecular bond structure gets deformed. So tension is due to deformation of the bond structure. So in a lattice, when you have atoms and if you apply force, the molecules will move inside and the structure gets deformed and they start pushing each other. So tension is also an electromagnetic force. So tension, normal reaction, friction, spring force, all these things at a fundamental level, if you see, are electromagnetic forces. Clear? Then, any doubts on this page? Now, now, when you talk about tensions generally, we talk about rods and strings. So rods, when you talk about a rod, they can pull and push. Meaning, if you take a rod here, M, if you look at the forces, the rod pulls, Mg is acting down. Same thing, you can keep the block M like this and you can keep the rod like this. In this scenario, the Mg is coming down and the rod pushes up. So rod can pull or push. So this is the thing, right? Whenever surfaces are touching each other, we call it normal reaction. When you have rods and strings, we call it tension. So strings, they can only pull. They cannot push. Meaning same thing if I take a string and attach a block. Tension, mg, string pulls. But the same thing, if you try to do something like this, put an M and try to put a string like this, the block literally falls down and the string becomes loose. Strings cannot push. The technical word this is, the string becomes slack and tension becomes zero. There, that is the main difference between a string and a rod. The strings can push, but strings can pull, but they cannot push. Think of a rubber band and a spring. Idea is the same. Rubber band can pull but cannot push. Springs can pull and push. There, these are the two main forces we will deal with. Normal reaction. So normal reaction primarily comes, when blocks are touching another block is on the ground, spear. So it's like solid to solid surface contacts. Strings and rods are like something connected by rods and strings as tension forces. Have a look at this. Then next thing. What is momentum? Symbol for momentum p bar is mass into velocity. That's a straightforward definition. But again, what does physically it means? Physically, what is the meaning of this? We had this discussion before, I guess. I don't remember, but let me see. Always, right? Whenever you define something in science, remember there's always one technical definition and there is one layman definition. Technical definition is good, but if you really don't understand what it means, then there's no point. You will just have a bookish knowledge. So, what is momentum? What does it signify? No, you need not give another technical definition. It can be an example. It could be something. You should have, when you think about momentum, you should get a feel, right, this is what it means. Let me ask you a question. If something is traveling with a speed of 1 centimeter per second, can you stop it? Right? If something has a mass of 1 gram, can you stop it? So if your local train is going with 1 centimeter per second, you'll go and stand in front of it. If a bullet of 1 gram is going with 1 kilometer per second, you'll go and catch it. See, 10 seconds, my answer change ho gaya. So the thing is, when I said 1 centimeter per second, you're not scared of the speed, you got scared of the mass. When I said 1 gram, you didn't get scared of the mass, you got scared of the speed. So what are you actually getting scared of? The product. It's not the mass that you're scared of, it's not the velocity, but the product. If you actually go and stand in front of a local train which is going with 1 centimeter per second, that's a very cruel death. It's like a good torture technique. That person who is under that kind of a train, you can see his body getting crushed centimeter by centimeter. He will feel the pain. So if you have a big enemy or something, that is how you can take revenge. So there you learned how to do a torture technique today. But anyway, so physical significance is higher the momentum. So if you ask me, sir, what do you think about momentum? This is what I think. Higher the momentum, more difficult to stop the body. So when you ask me, can you stop this? I will ask you what is the momentum rather than mass, and rather than only mass or only velocity doesn't give the full data. More difficult to stop the body. This is complete layman definition, but it gives you very good understanding. Okay, momentum matlab ye hota hai. So like this is what you need to learn. Everything you have a technical definition. You also have to have a layman definition. And then we know kinetic energy is half mv square. Multiply and divide by m. This we wrote in errors. So this is p square by 2m. Quite a useful one, comes a lot. Momentum is equal to 2 times mass into kinetic energy. And if you also see momentum, it's a frame dependent quantity. That means if you have a block here of mass m going with velocity v, and if you have a person A here at rest, and if you have another person B here who is going with you, if you ask A what is the momentum, he will say m into v. If you ask B what is the momentum, he will say m into v minus u bar. So depending on who looks at the block, they can give you different momentums. So momentum depends on the frame. Have a look at this. All clear with this? Any doubt so far? Then comes Newton's second law. Newton's second law says the force is proportional to force acting on a body is proportional to the rate of change of momentum. So the force is proportional to dp by dt. So if someone asks you what is Newton's second law, you say this. F is proportional to dp by dt. The proportionality constant F is equal to k into dp by dt. In SI units, k is equal to 1. Then force becomes equal to dp by dt. So if you say F is equal to dp by dt, it is wrong. And what is dp? d by dt into mass into velocity. So we can write force is equal to mass into dv by dt plus v into dm by dt. Product rule. And if mass is constant for a body, then we get dm by dt equal to 0. And then we get F is equal to m into dv by dt. And we know dv by dt is acceleration. So F is equal to ma. So this equation F is equal to ma is actually a blunder. This is valid only if mass is constant. Because in most of the problems, mass doesn't change, we ignore it. If someone says Newton's second law is F is ma, that's the biggest blunder. Valid only if mass is constant. If mass is changing, you can't even use this formula. But still, most of the cases, m doesn't change. We will see when m changes also. This is a good formula. If they ask you what is Newton's second law, you write this, proportional to dp by dt. Because if I do in CGS units, k won't be 1. Have a look at this.
So,
R.
so what does K depend on?
Depends on the units.
So like how did we determine that it's one in a sign?
Okay. In the equation S is ut plus half a t square, how did you find half? Just experiments. You do experiments, you figure out, you get the proportionalities. Constants you can't find, right, with theory. You have to figure out with experiments. In kinetic energy, how do you know it is half mv square and not mv square? The dimensions and all, you can find mv square tak aayega, but that half or what, you will never be able to figure out. So that things you have to do experiments and figure it out. Clear with this? Then so we have F is, like I said, we generally use always SI units. F is dp by dt. So integral dp will be integral f dt. This gives you change in momentum, which is P final minus P initial is integral f dt. This is nothing but area under ft graph. That means if you plot an ft graph, the area above the time axis is a positive area. The area below is the negative area. Example, this is a useful one, right? This is also called as change in momentum, basically, dpf minus this thing. The change in momentum is integral f dt. So example, let's say someone gives you an ft graph like this. Ten newtons, 10 seconds, 20 seconds, and 30 seconds. This area would be 100, this area would be 50, and this area would be minus 50. And let's say mass is given as 10 kg, and initial velocity is 5 meters per second. So the area would be 100 plus 50 minus 50, that is 100. This is change in momentum. So that is mv final minus mv initial is equal to 100. M is 10. So we get V10 is equal to 15 meters per second. There, they can frame questions like that. If you think about it, Ft is nothing but mass into acceleration, isn't it? So what does an AT graph give you? Change in velocity. So it is actually the same as AT graph. So have a look at this. So Ft graph gives you change in momentum. If you divide by m, it becomes an AT graph, and AT graph gives you change in velocity. Momentum by mass is velocity only. So it is almost the same thing. Have a look at this page. Let me show you one more example. Clear? Next thing. Let me show you one more example. They'll ask you a question like this. They will say, we have a trolley. Let's say mass of the trolley is 100 kg. And it started raining. And let's say rainwater is collected at a rate of 5 kgs per second. So every second, trolley ke andar 5 kgs ka rainwater is getting added up. And the trolley ka speed is 10 meter per second constant. So trolley is moving with constant speed. Now, in order to maintain the trolley car speed, someone has to apply an F external force. So question will be like this. Find F external to maintain the speed. Think of like this: when you're going on a cycle and your friend comes and jumps on the back seat, won't your speed suddenly decrease? To increase the speed, shouldn't you cycle more? Now, I'll show you normally how to do this thing. Listen. So what most people do now, they say like this. Since speed is constant, acceleration is zero. Therefore, and from F is equal to ma, therefore F is equal to zero. What is the problem with this? This is a
Mass is
blunder. Yeah. Since m is changing, first of all, you can't use this. F is not equal to ma. So you go back to the formula there. What is that? M into dv by dt plus v into dm by dt. So F is equal to, this term will be 0 because v is constant. V is 10 meter per second and dm by dt is 5. What is dm by dt? Rate of change of mass. Dm by dt is rate of change of mass. So every second, how much is the mass changing? So we actually don't need the trolley ka mass. We are only interested in the rate at which the mass changes. Therefore, we get F external is equal to 50 newtons. There. Simple mains level question. Most people goof up there at zero income. Most people won't even realize that the mass is changing, so you can't use the equation. This is the proper mains level question. Concept based. Have a look at this. So later on, right, we have a full section in center of mass chapter, something called variable mass systems. So there we will solve in more detail what happens when mass changes. We have a section on this, but let's see one more problem like this. Have a look at this example. All clear with this? Any doubts on this example? Let's say a question. You guys try this. We have a trolley. M is the mass of trolley. The rainwater is collected at a rate of lambda kgs per second. Someone is applying a force F is equal to F naught, which is a constant force. Initial velocity is 0. So you're starting this trolley from rest. Find the velocity of the trolley at time t. Let's get this. Similar question, but this time you're starting from rest. Think, take a minute or two. Anyone not clear with the data, please ask. Just give it a try, get some water and come. Hmm. Let's see the answer. FV lambda. God's dimensions भी मैच होना चाहिए. Arya, what is A? What is A? Who gave you that A? Don't bring new variables. जो है उसमें आंसर लेके आओ. Listen, I'll show you one. So we know change in momentum is integral f dt. Newton's second law. So what is change in momentum? M final, V final minus M initial, V initial is equal to, this is integral f naught into dt. What is M final? Mass of the trolley plus lambda into t. V final, and this is zero because initial velocity is zero, is f naught into t. So from there we get V final is f naught into time by m plus lambda t. So what is the final mass? The final mass has two components: mass of the trolley, which is constant, plus mass of the rainwater collected. So in time t, how much rainwater comes inside? Lambda into t. Every second you're getting lambda kgs. So after time t, this will be lambda into t. Make sense? So the trolley ka mass is increasing. The final mass of the trolley is m plus lambda t. Clear with this? You can't use f is equal to ma and then integrate. Because the moment you say f is equal to ma, that itself is gone wrong. Similar question, exact same thing, I'll just change few things. Let's say instead of force is constant, f is equal to f naught into t. T is time. What if you apply a variable force? Now find the velocity. Try, it is the same thing. I just made it little complex. So you're applying a force on a trolley which is increasing with time. Now find the velocity of the trolley after time t. Right, Vihan. Easy one, almost the same as the previous one, just a little change. Try. I'll give you another 30 seconds. Let's see. Same idea. Delta B is integral f dt. So this is m final, v final minus m initial. V initial is f naught t into dt. Final mass would be m plus lambda t into v. Initial velocity is 0. This is f naught t square by 2. There, so we get v final is f naught t square by 2 into n plus lambda t. Clear? Same stuff. So this is how you can play with variable mass systems. You can't solve them with a regular f is equal to ma and stuff. But more about variable mass systems, we will be seeing later on in a different chapter. We'll see even more detailed and more high level ones. But for now, this much you should have an idea. So don't blindly say if someone says F is equal to ma is always true, it is wrong. Clear? Next thing, Newton's third law. So for every action, there is an equal and opposite reaction. That's a bullshit definition. Because first thing you need to understand what's an action and what's a reaction. Let's say I shout on Vojas, right? He gets angry, he brings 10 rowdies to beat me. Now, here the action is I shouted. The reaction is he brought some 10 rowdies. So the thing is, the reaction always happens because you did something. You're getting it. Now you tell me, let's say, no, if I slap you, right? Tell me one thing. Did my hand touch your cheek first or did your cheek touch my hand first? Now, can I say like this? Your cheek is harming my hand. My hand is paining because your cheek is hitting my hand. Same thing, right? Instead of you saying, sir, you slapped me, that is wrong. Your cheek is actually hitting my hand and my hand is hurt and I'm feeling bad about it. See, the thing is, the moment when you touch a table, you're touching the table and the table touches you at the same time. So there is no meaning of one is action and one is a reaction. When you say action reaction, it is like because I touched the table did something to me. That doesn't happen. Both the things occur at the same time. So the word action reaction doesn't make sense. But all books it is written, it rhymes well. So people just used it. So the actual definition goes like this. You will see that in books and all, so it is fine, but at least you have an understanding. So when two bodies interact, the force between them has to satisfy a few conditions. First thing, they should be equal in magnitude. Opposite in direction. So till here it is the same thing. Along same line. If both the forces are not along same line, the body will start rotating. You'll get a couple. Also studied in school. Two forces, equal and opposite, but with a distance between them. They should act at same time. Just imagine you're sitting on your chair. The time they don't act at the same time. You know what will happen? So when you sit on the chair, first you'll go down the chair, then the chair will push you, you'll jump. Then the chair will slowly you'll go down, then you'll jump. So in your chair, you'll be just jumping up and down non-stop. If there is a delay. Getting it? They must act on two different bodies. They must be of same nature. Same nature meaning both should belong to the same category of forces. Meaning if one is gravity, other should be gravity. One is electromagnetic, other should be electromagnetic. So when you say a Newton's third law, it has to satisfy these 6 conditions. Let me show you a question on this, or a good theoretical question. Let's see. So let's say we have a block on the table. Block is at rest on the floor. Now, when you try to draw the forces acting on the block, you have mg and you have the normal reaction. So my question is, are mg and n action reaction pair? So we'll not use that word, but are they a pair of forces? What is the catch? Now, what do you think? Are they an action-reaction pair or not? Why? What is the reason? Now, first, let's see. If you see this, look at the first condition. They should be equal. Chalo, let's assume they're equal. Right? Second, they should be in the opposite direction. Fair enough. Same line. Fair enough. Same time. Fair enough. On the different bodies, that is wrong. Fifth condition is gone. They act on two different. They should act on different bodies. They're acting on the same body. Sixth, they should be of same nature. That is gone. Gravitation is the mg is gravitational force. Normal reaction is electromagnetic. They're not of same nature. So N and Mg are not a pair. Fair enough. So, but where is the pair then? Remember, in nature, forces always come in pairs. You can't just have a single force. So if these two are not an action-reaction pair, where is the action-reaction pair then? If these two are not a pair, the pair is somewhere else. Where is Mg ka pair? One thing is clear. This is not there. This is not an action-reaction pair. That is clear. Vihan. Think, others think. I'll give you another 20 seconds. If these two are not a pair, there is a pair somewhere. Kaha pe tha wo pair? Where is that pair? You will always get forces in pairs. You won't get a single force hanging. Center of mass. See, the thing is, when you take the block here, M, and if you take the Earth, tell me one thing, who's attracting the block? The Earth. So this is the gravitational force on block due to Earth. And we studied in gravitational force in school. You studied the two forces always attract each other. So the block also attracts the Earth with mg. This is the gravitational force on Earth due to the block. But this force is so small, Earth is so big, that is the reason Earth doesn't move. So if the Earth attracts the block also will attract the Earth. So there's an mg pair on the Earth. Are you getting it? Who is pulling the block down? The Earth. So block also pulls it up. So these two are a pair. Now look at this. Mg both are equal. Yes, they're definitely equal. Opposite, yes. Different bodies, yes. Same nature, yes. These are a pair. Now if you look at the normal reaction, this is N and this is N. The molecules on the surface of the block and the ground are repelling each other. There are two repulsions. So these two, right, is the normal reaction between the body and the ground. So this is the pair. So this is a normal force between the block and the ground. So when you're standing on the floor is pushing you up. In return, you're pushing the floor down with the same electromagnetic force. It's a repulsion. So the N on the block and the N on the floor are a pair. These two are a pair of forces. I hope this is clear, everyone. The N and Mg are not a pair. If you're having an Mg, there is one more Mg somewhere. That is generally the planet. And when you're standing on the floor, you're pushing the floor down and the floor is pushing you up. That is an electromagnetic repulsion. Those two are a pair. Clear with this? It's a good theoretical question. Most people think N and Mg are a pair because they look like equal and opposite. So if you just write that one statement, right? Newton's third law is forces are equal and opposite. So this satisfies equal and opposite. The problem is that then things go wrong. It has to satisfy all those 6 conditions. Is this clear, everyone? There, that is your three laws. And you can see each law did give you something. The first law gave you the different types of forces. Second law talked to you about the F is equal to ma and variable mass system. Newton's third law, you can see. Then next thing is free body diagrams. Easy one, but quite an important one. Any doubt so far? Please ask me. All clear the third law? Great. Free body diagram or FBD. So what is an FBD? So free body diagram, it's a pictorial representation. It's a pictorial representation of forces acting on the body. Now be careful. In this, we should draw forces acting on the body, not the forces given by the body. We should not draw forces given by the body. For example, let's say you're sitting on the table. Now think about it. If I ask you to draw your FBD, what will you draw? Your chair is pushing you up. That we will draw. You're pushing the chair down. That we should not draw. We should draw the forces acting on you, right? You're putting your hand on the table for rest. The table is pushing you up. If you're wearing glasses, the glasses ka weight is pushing you down. The earth is pulling you down. So you have to write all the forces acting on you. Getting it? So we will see some examples. So steps to draw an FBD. First thing, choose your system. Let's say if there are 5 blocks, you choose which system you want to draw an FBD. That is your call. Choose your system and draw the body with the same orientation. Meaning, if someone gives you like this, and they ask you to draw the FBD of this, so triangle will look like this. So B, you draw it the same way. Don't rotate B. Don't draw B like this and say I made it flat. So if it is at an angle, keep it at an angle. Draw the same size. Some people, right, in some books, they replace the whole body with a point and they draw the forces. They call it a point FBD. Don't do that. It's later on when we do rotation mechanics, it becomes a big mess because the lengths and the dimensions will matter later on. Right now, it won't matter, but later it will be quite useful. So draw the body as it is. If it is at an angle, at an angle. If it is straight, it is straight. However, it is, draw it the same way with the same orientation. That is your step 1. Okay, then draw the weight vector mg downward. Third, for every point in contact with a surface, draw a normal reaction with appropriate symbols. So if you're touching at 2 point, then you write N1, N2. Example. If you have a sphere like this, you're touching here, you're touching here, and you're touching here. So there are 3 points of contact. So if you ask you to draw this sphere FBD, then I will draw, this is one normal, another normal, and 3. Remember, for a sphere, the normals always pass through center. So I'll draw 3 normals. For every point in contact, you draw one normal. For every string, spring, and rods, draw tension and spring forces. So if there are 4 strings connected, put 4 tensions. If there is 2 springs, then put spring forces. Spring forces we will in more detail later on, but for now, there. That are the steps for an FBD. Have a look at them. Clear? Now, let's see some questions. So I'll give you some shapes and we just have to draw the FBD. Hope everyone has finished constraints ka sheet. Easy, able to get most of them, I suppose. Let's see, we will discuss them, what we don't get today. Now, so let me give you 1 or 2 examples and then I'll give you more you can draw. So see, first one, let's say we have M1 and M2. So I have to draw the FBD of M1 and M2. So listen how we do this thing. So first for M1, just think of like this, right? You're sitting on a table with a bag in your lap. So M1 is the bag and MT is you. So when I have to draw FBD of M1, just think about M1. What is happening with M1? The gravity is pulling down. And what are you doing to the bag? You're pushing the bag up, isn't it? If the bag is in your lap, what are you doing to the bag? You're pushing it up. That's it. There are only 2 forces. You're pushing the bag up and the weight is pulling down. Now, if I ask you to draw the FBD of you, the bag is pushing you down, the earth ka weight is pulling you down, and the table you're sitting, the floor is pushing you up. Is this making sense? There are 3 forces on M2 and there are 2 forces on M1. That's it. That is how you draw the FBD. Now, today, don't worry about forces, acceleration, equilibrium. Kuch nahi, just forces. We'll just draw the forces. Later on, we will combine one after another. Then we will bring acceleration and all that stuff. So if I show you one more, if someone asks you FBD of M1, FBD of M2, FBD of M3. So M1, its own weight. M2 is pushing up with N1. M1 also will push it down with N1. That's the Newton, that's the pair. M2G, its own weight. This would be N2. N2 will push N3 also down. This is your own weight, and the ground is pushing up with N3. Please check. That's it. So FBD, you just draw the forces acting on the body. Please have a look at A and B. Ask me if you're confused. Don't worry about components, nothing, just the forces. Can you draw FBD of M1, M2, M3? So we got an incline, and on top of it, you kept a triangular wedge like this, which can slide, and on top of it, there's a block M1 again. Just draw the FBD. Don't think too much. Whatever you think, you draw, right or wrong. I'll show you, then you can verify your answers. That's the best way to learn. Just draw whatever you feel. I'll give you 20 seconds and I'll show you. Don't take too much time. Clear? Let's see. So we have this. So just check whether you got it right. You got it wrong, see what went wrong, and if you got it right, then great. So I'll start from M1. You can start from any word. Now, one more thing. If I say N1, but you used N2, that is okay. Just make sure the pair should have both same symbols. So M1, there's M1G and N1. So that N1 will push M2 down. M2G will have its own weight. And this would be N2 here. This would be N2 here. This will be your own weight M3G, and this will be N3 here. Clear? All got this? Easy? Let's see a few more. That's a wall. That's M1 and that's M2. Get them both. Try. I'll give you a minute. Done. Let's see. Let's say this is N1, your own weight M1G, N2, N2, M2G, and let's say this is N3. Now here, if you look at the points of contact, there is 1, 2, 3, 4, 5, 6. There are 6 contacts.
In the first diagram, N1 is the wall ka.
Yeah. N1 is the wall count. So if you look at M1, your own weight M1G, this wall, let's say, is pushing with N1. This is N2. Now our symbols could be different, but that's what I'm saying. If you say this is N2, make sure this is N2. This is M2G. This is N3. This is N4. Now remember, all these N's will pass through the center. This is N4. This is N3G. This is N5, and this is N6. So if you see the lower two balls, there are three normal reactions. Please check your FBDs. Now, Surya, clear with this? Vignajit, Nikhil, any doubts on this? Turn in the page. Any doubts? Anyone not clear, please ask. I know it's an easy stuff, but be very clear with each and everything. Because in the final thing, if you go for 1-4, the whole thing will go for a toss. M1, M2, M3, three wedges. That angles and all, later on we will see when you take components in the next class. It will be useful then. Get them all, you got a minute. Hmm. M1G, N1, N2, N2, M2G, N3. N4. No, only for the blocks we have to draw the FPT. So if you look at here, it is the same string, tension, tension. You can directly draw it here only. So M2G, M1G. So if the tension is string is same, you will take the tension to be same in this entire thing. So directly you can just draw it and leave it there. So on each block, there are only two forces, tension and M1G. Like I said, don't worry, it will move up, down. We are just doing forces today. Later on, we will see how these things will move. What is the acceleration? We will combine constraints and FBDs and everything. Here, what you do, if you say this is tension T, this is tension T, you can start up also tension T, then this will be 2T. So this will be 2T. This will be M1G. If you start from T from the top, this will be T by 2, T by 2. It's fine. When we actually do the problem, values will come same. End of the day, answers will come out to be same. Check it out. That's it. This is the FBD for the blocks. Yeah, here I'm asking you to draw FBD of the blocks. Now, why will you consider pulley guard? Question is FBD of M1, M2, M3. Where is the pulley in M that M1, M2, M3? No? All clear? Pulley will come. Next one. Now draw. Let's see. This is a good one. So here, what you're saying was just now it comes. Now M1. Now this is the thing you have to be careful. When you're drawing the wedge here, understand one thing. The pulley is fixed to the wedge by a rod here. It is just not hanging there. It is connected to the rod. Means whatever forces are acting on the pulley, they will act on the wedge also. So this is tension. The weight is M1G. Like I said, right now we are not dividing components and stuff. This is N1. This is N1. This is a mistake most people do. They forget the tensions here. You have to include these tensions. That pulley is part of the wedge. You're getting it? So that has to be included in the system because it is rigid. Fixed pulley is fixed to the wedge. The pulley and the wedge cannot be separated. So the pulley is part of the system. So if you have pulleys which are fixed to the wedge, you have to include them. But if the pulley is just hanging like this, here see, these pulleys are useless. We are not drawing FBD of the wall, the ceiling. So if pulley is fixed to the wedge, we have to include them. Because whatever force is acting on the pulley, that will come on the wedge only. You have your own weight, M2G. You have a normal reaction in ground. This thing will be, if you see, this is tension T. So this is tension T. This will be 2T. So this is 2T and this is M3G. Check. J is the hanging block in the hanging block is touching, na? There I showed it is touching here. If it is not touching, I will draw like this in air. If you remember, we did a constant equation for this, right? भूल गया क्या? Same question. Try. Another 30 seconds, I'll show you J. So look at the big block. That wedge has to be, the pulley has to be included. So totally, there is one tension here, tension, normal reaction because they're touching each other. There is one more tension here. Remember, there's a string attached at the bottom also. Your own weight and the normal reaction due to ground. Total, there are 6 forces. Hope everyone has included everything. Check. And for that block there, so tension, normal reaction, your own weight. Easy. So see whether you got 6 forces for the big block. There are 3 tensions on the big one. Any doubts on this page? Please ask me. I'll send you a small sheet on FBDs also. You can draw like, they're like easy if you see it's just about drawing. But the thing is, you mess up one force, right? You will go up the whole thing. We did constant for this also. So this pulleys will be included. Now be careful, this tension will be like this at an angle. This will be normal reaction. This will be of weight and this will be the end ground. That last pulley ka thing you have to be careful. This will be tension, this will be N. Mg and this will be your N. Clear everyone? There, that is about FBDs.
So from capital M, like 6 T's will be 6 tension.
6 tensions?
So 6 or 7.
7, na?
Just we take that angled thing also.
मतलब string है तो see wherever the string touches there's a tension there. So it is entering and going like this ना तो tension और tension ऐसा होगा ना, it pulls that way.
Okay.
अभी यहाँ पे देखो कैसा किया हमने, देखो यहाँ पे एंगल में तो किया ना टेंशन. So if the string is going at an angle, take tension. See, tension is always along the string. All clear with this? So there, that is about FBDs. Okay, so with that, we'll wrap up for the day. We'll discuss the paper and the constraints ka sheet. So next class, when we catch up, what we will do equilibrium. Remember, we did this in vectors. You can revise the vectors ka notes in equilibrium once. So we will do problems based on equilibrium, and then we will go ahead with things. Now things will start moving after this. So if you have understood FBDs and if you understood constraints, your basics are clear. Now the actual stuff starts. So yeah, we will take another 3-4 classes, but the main part is done. The theory part is done. Like the basics are done. So the basics are 22 problems. So do make sure to go through all this stuff, right? And I'll send you a small FBD sheet also today.